We're going to take a look at Google Kickstart 2020 round C. So the round is already finished, but I haven't looked at these problems before, so new for me. So what's going on? So this is the first problem. We have an array of positive integers, and we want to find basically a straight, right? Like, k minus 1, all the way down. I see. And k is between 2 and n, a is up to 10 to the 5, and the length of the array is 10 to the 5. Right, so the point is that we can't afford n squared, but we're looking for like this extremely specific pattern. So this should be pretty straightforward. Maybe we can just do hashing. That's probably true. This is kind of like a string search problem, if you think about it. Right, you're searching for like this specific substring, like 1 through k reversed in this array. Okay, this is C, and it's column A, T, and then N and K, sure. Oh, actually, I think we can just check everything. And the point is that we can like skip forward when we get a mismatch. Yeah. Right, in particular, like we only need to start looking at the positions which are indexed k. Which are k's. Yeah, so that will actually be fast. Okay, that's easy. So is that it? We just do the countdown, and then we skip this index. We never want to look at it again, actually. And if we got all the way through the countdown, then we are done. There's some subtleties around this. Probably easier to go this way. That's right. compiler here. We forgot to declare LL. That is fair. Two, 0, 1. What do you know? Okay, so it's judging it. Let me try to explain what's going on. Right, so we're looking for like k down to 1. So this is keeping track of like the countdown, right? So we're looking for a k, and well, we match the k, and there's stuff left to look at, and we're not done with the countdown. Go to the next number, decrease the number in the countdown. At the end of this, right, there's like a bunch of ways this could have ended. Either we got through the whole countdown, or we reached the end of the array, or we had a mismatch. So if we got through the end of the countdown, then that's +1 to the answer. And then we need to start looking at the next position that is a k. Right, we need this to like not get stuck forever. But yeah, you might think that you could just do like I++ here, but that's not actually right, because if we went through the whole countdown, we might be on the beginning of another countdown. We wouldn't want to miss it. But if we didn't move at all because the number at the current position wasn't a k, then we need to make sure to increment. So anyway, that's what this is doing. And it looks like it was right on both test cases, so that's nice. Let's move on to problem B. Stable wall. Oh no. Looks like geometry. Okay, so we have polyomino. It's a connected like shape in a grid. And we want to or have connected n polyominoes into a rectangular shape. They're all labeled A through Z. You created I guess this rectangular wall is the same as a rectangular shape. R rows and C columns. Send it to Celine, who wants it to be stable. And it's stable if we can add them one at a time such that like gravity works. Right, we never have a square hanging over the air. I see, so we should give the order, right? We're given some rectangle made up of letters, and all the letters are all from connecting components, and we're supposed to give an order of the letters that like constructs the rectangle. So for example, here we can construct the Z because they're all on the ground or supported by another Z, and then after we put the Z, you can put an O, and then after you put O, you can put A, and then after you put A, you can put M. And I believe you could flip A and M as well. Yeah, I'll put any of them. And if it's not possible to do that, then I'll put -1. Why is this one not possible? Right, we can't put down X because the X is hanging over air. We can't put down O because the O would be hanging over there. And we can't put down F because it's not even touching the ground. So there's nowhere to start in this one. This one, similarly, you'd like to start with the X, but like this one and this one are hanging over the air. This one you can do, there's like overhangs, except you can start with E and then D and then C. Yeah, okay. And they say, yes, COMA is also possible. And this is the only possible, sure. Okay, so it's 30 by 30, and in the small case, n is less than or equal to 5, so you can just brute force it by checking all permutations. In the large case, n is up to 26, and you can't go through 26 by 12 permutations, so we gotta do something a little bit clever. We can probably just like brute force it, right? Just like keep looping over the letters, and if you find a letter that you can put down right now, just put it down. There's no harm in doing it. And if there is no such letter, then you lose. So the only question is whether or not you can put a letter down right now, and I don't know, it's not that hard to do. Okay, so let's do that. Now you just need to check if any of the letters are hanging over empty space, which is, I think, not going to be that challenging. symbols. T, R and C, and then the actual grid. Okay. So these will be the squares that you've successfully placed so far. Sure, this will be our answer. Oh, is n? No, n is not a thing. So we want to check if we can place this letter, and also I guess if it has anything in it. I guess we should check if we have not already placed it as well. Okay, so the ones on the bottom are okay. Those are the ones with r equal to r minus 1. So after we've done a round, we can check if we're done. So if we're not done, and if we haven't changed, then it's impossible. Right, which is something else we can place. If we are done, obviously it's possible we found an answer. And one of those two things should eventually happen. Vector string what? C or something? Let's see. This is in fact a double vector, and this is a double vector. Those error messages. I don't know about that. I see. Not just if it's not already placed, but also shouldn't match ourselves, but the Z is allowed to stand on the Z. That looks better. Zone, -1, EDCBA. Cool. This is C++. Yeah, so the idea is we're just going to keep looping forever and just try placing each possible character. So how do we tell if we can place a given character? Right, so we're going to try all 26 possibilities. This is the character corresponding to this index. So this is whether or not it's allowed to be placed, and this is whether or not that character actually exists, right? In like this array, there's no B. So go through all the whole grid. If we find something that matches, the one that we're interested in, then we do actually have it. If we've already placed something, if we've already placed that square, then we're already good on this character, right? We already put it in, so we can't put it in again. And then this is the more interesting check, is that if it's sort of floating on the air. So if it's not on the bottom row, right? If this were true, we'd be on the ground, and there's nothing underneath it, and the thing underneath it is not itself one of these characters, because we're allowed to rest. You're placing like the whole block at once, right? So like the Z is allowed to be on top of the Z. Then you're going to be placed on the air, which doesn't work. That's like unstable according to the condition. So if we actually have some of this character and it's okay to place it, then actually place it. So mark down that we actually did something. Write down that we actually placed this character, and then for all of those squares, mark down that there is sort of a solid block there. So after you've done a full loop of trying to place everything, you can check if you're done, right? That is, if you've placed all the squares. If you are done, then you print out, the answer, right? We've been keeping track of the order that we place things. If you're not done and nothing has changed, then it's hopeless, right? You tried every possible character, none of them could be placed, and the wall still isn't done, so there's nothing to do. And it is right, so that's nice. Yeah, so we have this while loop that's handling each case, and then we break, once we print out the answer for a case, we break to go to the next case. So that is the second problem. All right, the third problem. So we have an array of integers. They could be negative, and we want to find the perfect subarrays. How many subarrays are perfect? And it's perfect if its sum is a perfect square. Notably, none of the perfect squares are negative. Okay, and it can be n up to a. The a's are quite small, actually. They're only up to 100, negative 100. And n is up to 10 to the 5, so we can't even afford to look at all of the subarrays. Interesting. So in this case, the only answer is these two add up to 4. In this case, I see 9 itself is a perfect square, 1 is a perfect square, and this whole thing adds up to 100 apparently. Yep, that's true. I see. And here, there's a bunch of zeros, which contribute a lot. Interesting. I can do this in n squared, right, by just looking at every subarray once and using prefix sums to get the sum in constant time. That's good enough for test set 1, but it's not good enough for test set 2. So how do you do test set 2? Well, so one thing to notice is that there's not that many perfect squares that are even possible. Well, there's 1,000 or something. Right, because it's of length at most 10 to the 5, and each number is at most 100. So the total sum is at most 10 to the 7. And there's, square root 10 to the 7, 10 to the 3.5, 3,000, squares less than 10 to the 7. But then, that's a decent number. Well, so if you do take prefix sums, then the a contiguous subarray is just the difference of two elements, any two elements. So the question is, how many pairs are there such that the difference is a perfect square? And right, if we just wanted the difference to be some specific number, we could do that with a map. In linear time. So this is n times square root 10 to the 7 time, which is maybe fine. I don't know. I think that's sort of reasonable. Especially, yeah, okay, so you get 6 seconds per case. That's kind of a lot. Okay, so yeah, we just have an array, fine. this is right. Just don't know if it's fast enough. But I guess we'll see. Simplification. One, two, three. Something's wrong. G6. Yeah, so this one is correct. Nine and one. I got myself confused. Okay. So hopefully this is fast enough. So the idea is right here, and I think it's relatively clear. So we just keep track of how many times each number has appeared in a map. Ooh, I wonder if it could be an array. Oh, it's wrong. Really? Okay. Well, maybe I'll try and describe the idea and I'll figure out why it's wrong. Okay, so we do prefix sums. Starting with the empty sum is 0, and then the sum of the first P1 is the sum of the first element, P2 is the sum of the first and second element, Pn is the sum of the first n elements. M is going to keep track of how many times each sum appeared. And then for the sum to be a square, right, we're going to iterate over all the possible squares. Wait, this is the far side of the sum. So if this sum is supposed to add up to k squared, then we must have pi. I should really change this to j so that it's clearer. Anyway, pi must be, yeah, I'm just going to do that. This should be j, 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 j. Okay. So pi must be pj minus k squared. If you just do like a little bit of algebra on this. Not that much algebra. And so the number of intervals ending at j is just the count of how many times pj minus k squared has appeared. Not sure about this claim. I don't know. And then we increment the count. Right, because now we, our value can be used by later guys. Minus 1 plus ai minus 1, that should be fine. This is fine. Zero, 0, 1, and then 1, 4, 9 all work. That's right. Is there an overflow issue? No, because a is small. Oh, I am sort of assuming. Yeah, this is garbage, right? Like the total sum might be negative, but you could still end up with some perfect squares if there's like a 0 in the array. So this is stupid. What should it be instead? Like this. Right, that's like the maximum possible sum in the array, which seems more sensible. Right, like the bad case before was something like, negative 100, negative 100, 0. I would have said 0, but in fact, like, this one works. Yeah, so the argument's the same as before. It's not super clear if this is really fast enough. I suppose you might, yeah, you can probably just do M as an array instead of as a map. That would be faster because these values can't get that big. Right, like this is at most 10 to the 7, so this is at most 10 to the 7, this is at most 10 to the 7. So if this array is just like 2 times 10 to the 7 large or something, that should be fine. And that, I think, will be fast enough. So we just need to, it's taking quite a while. It's probably, maybe a sign is too slow. Let me switch to a vector. Right, so this is just me centering it so that I can start at negative 10 to the 7, or negative 100n, actually. And same thing here. Yeah, that still works. Memory limit exceeded. Really? I'm not even using that much memory. 1 gigabyte. How could I possibly be using a gigabyte? Well, anyway, if I have like these, yeah, this one should be fine. I guess maybe unordered map is bad somehow. But here I'm using like 200n memory, which is 10 to the 7. Should be okay. I guess it's cutting it a little bit close. Right, 10 to the 7 long longs is, but I mean, this could be int actually, if I really need to save the space. Right, okay, yeah, that passes. Okay, yeah, that was kind of interesting. So anyway, this idea is fine, but we don't want unordered map, we just want vector because, right, this condition is actually important. The partial sums can't get too big or too small. So we can just give a slot for each possible partial sum rather than having a map. And like vectors are just much faster than maps, so that helps a lot. And also apparently less memory. Okay, that was problem C. What's going on with problem D? Candies. So we have n candies, and each one has a sweetness, and we are going to perform, oh gosh, Q operations. Some polynomial hash, okay, sure. So either we want to update the sweetness, or we want to query this weird function of a subarray. Oh, it's alternating, subtracting. Ugh. Data structures. Okay. Most 5 update operations. Well, if there are most 5 update operations, then you can just. Oh, I see. You still need to do the queries quickly. Yeah. So suppose that there were no update operations. How would we do these queries quickly? Yeah, I mean, it kind of seems like you just want to store the alternating. let's see, 1 times 0 plus 2 times minus. Right, you could do that, and then equals sj minus s I minus 1. That would equal, oh gosh, I plus 1 times ai. That would give you like the I to j part of that. Right, so the query answer is basically this. So that's fine. I think we can just store these in a Fenwick tree. And then answer the queries. And you need to like multiply this by -1. Depending on -1 to the I or something. Something like that. Okay. Right. It's nice that I know Fenwick trees now. Then n in q. AI. In fact, it'll be, I think, better to one index the array. Okay, I believe that's a Fenwick tree. So this gives us the operations. This is what the Fenwick tree does. So B is going to store the array. S stores I times the array, which is sort of a version of this sweetness score. And then I believe we can use that to answer the queries. So now we have a bunch of queries. Do the updates first. I think they're easier. X and V. Okay. Let's say J and X. It's all one index, right? Yeah. So we want to get the current value at that position, which is just like this sum. This is how you recover elements from partial sums. And then we want to change it to x, but it's just the same as adding x minus cur to it. And also we should change s. So the value used to be, so it should be x times j minus cur times j. Okay. L and R, sure. Okay, so it should be s dot sum r minus s dot sum l. So that gives l minus 1. Now we have a L. Oh, we need to do the negative thing. So this should be negative sometimes. we actually like want the alternating sum or something. Yeah. Yeah, okay. That I will just store the array, I think. Let's do it that way. Okay, so if L is odd, then if L is even, then we need to multiply by negative 1. That is completely wrong. Well, actually case 2 is correct, but case 1 is completely wrong. So it was 398. That's fine. So that should have been 9. What did we actually get? Okay, we did get 9. That's good. SI. That seems not as good. This should be 1 plus 1. Okay, we got 9, we got 2, we got negative 19. I think that's negative 8. We got negative 3. And that's negative 3. Okay. That looks fairly reasonable. Negative 8, negative 3. Okay, so what's going on here? This is a somewhat uninspired data structures problem, I would say. So we need to support 2 operations, just update an array element or compute this weird sum over some subarray. N and Q are both 10 to the 5, so we can't just do sort of the naive sum here. We have to do something clever. Right, that would take like 10 to the 10 operations, which is too much. So we use a Fenwick tree, which, 2 Fenwick trees actually. So the tricky part of this problem is seeing how to support this with a Fenwick tree, and then also knowing about Fenwick trees, or knowing how to code them, I would say. So this is part 2. This doesn't depend on the problem at all, right? This is just a good data structure to know. A Fenwick tree takes, some parameter n, how long the array is, and then it lets you sort of maintain this array, and it gives you 2 things to do. So you can add something to an element of the array, or you can compute a partial sum of the array. And so there's relatively short code that supports both of those operations. It's a little bit hard to understand exactly how this code works. I have a video on it if you're interested. But basically you just keep adding the lowest bit or subtracting the lowest bit and doing stuff with the elements. Anyway, so assuming that you had a Fenwick tree, how would you use it to solve this problem? So we're going, so you have to start at the end. So this is what we want, right, is this alternating sum. Starting with AL is 1, and then AL plus 1 gets negative 2, and then AL plus 2 gets 3, all the way up to AR. And so the way that we're going to get that is we start with, so we start with this alternating incrementing sum, which we store in S. So S is going to store plus or minus I times AI. And so if you query this subarray of S, right, this is how you get a interval sum from a prefix sum. If you query this subarray, you get L times AL minus L plus 1 times AL plus 1. And this may actually be plus or minus depending on the parity of L, which we'll solve later. So this is sort of similar to what we want, right? It has this plus or minus and incrementing index, but instead of starting at 1, it starts at L. But that's no problem, because we can just get the total sum, the regular sum of AL plus 1, or actually not the regular sum, the alternating sum. Right, so just sort of blank out all these coefficients, right? AL minus AL plus 1 plus AL plus 2, and so on. That you can get with a Fenwick tree that just stores, the alternating sum, right? So plus or minus AI. And so then if you subtract L minus 1 times this alternating sum from what we had before, now we get something that's very close to what we want, right? Because this L turns into 1, this L plus 1 turns into 2, the L plus 2 turns into 3, and so on. The only remaining issue is that the alternating, right, we actually want to start with AL being positive, whereas the alternating sum here started with a 0 being positive. But that's fine. It's just that if L is, or actually a 1, because we have 1 index in here, if L is odd, then it's already fine because all of the odd indexes are positive, and if L is even, we just need to flip everything by -1. So that's what we're doing here. And so that is the answer to the query, is like this construction. And okay, so how do we do the updates? So now that we like have this plan for answering the queries, we know which like Fenwick trees we're going to use and what they need to store, right? Because we needed to do like 2 range sums here, right? Here and here. So we need a Fenwick tree to support both of those. So one of the Fenwick trees is going to need to support plus or minus AI, and one of them is going to be plus or minus I times AI. Yeah, and we're also going to store the vector itself for reasons that will soon become clear. So the way that the updates work is, well, we want to set aj to x. So Fenwick trees don't do setting, they do adding. So to set, we need to know what the current element there is, and then we can add x minus the current element, essentially. Except that we need to modify it with like the operation that it's storing. So we want this to be x times the alternating thing, but it's currently cur times the alternating thing, so we can add x minus cur times the alternating thing. This one we want to be x times j times alternating thing, but we currently have cur times j times alternating thing, so we can add, x minus cur times j times alternating thing, plus or minus 1. So that updates the Fenwick trees, and then we should update the array itself. We don't actually have to store the array. We could extract the element by like b dot sum j minus b dot sum j minus 1, but then you have to multiply by plus or minus 1, so it's just easier to store the array to code. So that's how we do the updates. And initialization, initially the Fenwick tree starts out as like all 0, so you can just add like the starting values of the array to like initialize it. Right, so we just read in the array, and then we set, okay, bi is supposed to be ai times plus or minus 1, and si is supposed to be ai times I times plus or minus 1. So you can think of this also as just like an additional set of updates. That's right, this is basically the same code as this, although slightly simpler because we know that the code is 0 here. Yeah, so that is the last problem in this Kickstart round. So that's it. Some problems. Call it a day.